Hello and welcome to my channel again. This is Mohamad Al-Darazy. In this video I'm going to be discussing document 4, the sensory receptor and nerve impulse, part of chapter 9 of neurophysiology in the Lebanese back LS book. Now I usually explain this lesson through an interactive PowerPoint slideshow coupled with a worksheet so that my students get to watch simulations of the experiments in the book and to collect the data, and then afterwards they get to come up with their own conclusions. In this video, I'm going to show you the how this works and the conclusions that the students are supposed to get at the end. So let's start with the introduction in the book. They said experimentally it is possible to stimulate each point of a neuron or of an isolated nerve to obtain a nerve impulse. This sentence relates to what we've been doing in the previous activities in documents 2 and 3 in particular, where, if you remember, we used to stimulate or apply any stimulation at any point of the nerve fiber. If this stimulation was effective, meaning equal or above threshold, an action potential should be generated and detected. But in vivo, meaning in the real live system, the living system, the genesis, the formation of these impulses, the action potentials, is done only by specialized neuron structures. This is because we have to realize that we're usually in the body dealing with real sensations like sound, like temperature variations, like pressure, like force. So these are the things that we usually detect and the body responds by forming action potentials for. For that reason, we need structures called sensory receptors. So what are these structures and how is an impulse triggered at the level of these structures? So first of all, with the definition, the function of receptors, sensory receptors, is to convert the different forms of energy into electrochemical energy or action potentials and transmit them to the nerve centers. So let's take the example of the photoreceptors in your eyes, for example. These deal with light energy. They collect light from your surrounding and they convert it into an action potential or several action potentials, which are in reality electrochemical energy waves. Because they have electric properties, they can be detected by oscilloscopes, voltmeters, etc. And in reality they are formed of changes in the chemical, the ions, the distribution of these chemicals in and out of the cell. So a receptor absorbs different forms of energy, like light, like temperature, and forms action potentials. Then it sends these action potentials to the nerve centers, like the brain and the spinal cord, for these nerve centers to interpret these sensations and do whatever it sees fit. So part 1 of the interactive PowerPoint, I usually supply my students with an image similar to this one. And as you can see here, we see different sense organs in the skin. I ask my students to collect the different names of these receptors, like the thermoreceptor, the myosinal corpuscle, nociceptor, Pacinian corpuscle, and its location within the skin, and also to pick out the sensation that each of these sensory receptors can detect. So this is what I usually ask my students to do, and this is the table that they're supposed to fill. Name of the sensory receptor, we have the thermoreceptor, the myosinal corpuscle, the nociceptor, and the Pacinian corpuscle, just examples. Of course, we have other receptors in the body. The skin layer in which it is localized, in the dermis, most of them, and the Pacinian corpuscle in the hypodermis. The detected stimulus, heat or cold for the thermoreceptors, touch for the myosinal corpuscle, pain for nociceptors, and pressure for the Pacinian corpuscle. Part 2. Now in the book they elaborate further on the Pacinian corpuscle, so this is what we're going to do now. The Pacinian corpuscle, as we saw in the previous slide, is located in the hypodermis and detects pressure. So it's approximately an oval cylindrical shaped, 1 millimeter in length. This is how it looks. You can see here I used an image of an onion because you can clearly see it has very similar characteristics to an onion in its shape. It's oval and it has several layers. So the entire corpuscle is wrapped by a layer of connective tissue from the outside. Its capsule consists of 20 to 60 concentric lamella, including fibrous connective tissue, separated by gelatinous material, more than 92% of which is water. So it's practically like a balloon filled with water. So it's gel-like from the inside. And if you haven't already guessed, it's called the Pacinian corpuscle in reference to the scientist who discovered it, Mr. Filippo Pacini or Pacini. So it senses pressure, of course not this type of pressure, not peer pressure, It senses pressure mechanical force which is applied on the skin. So the Pacinian corpuscle are rapidly adapting receptors that detect gross pressure changes and vibrations in the skin. Deformation in the corpuscle, because remember I said it's like a balloon filled with water. So when you press this balloon, it's going to deform. This deformation causes action potentials to be generated. How come? Because this pressure opens pressure-sensitive sodium ion channels. We've already studied ion channels before in the previous documents. We said we have chemical-dependent ion channels. Some of them are ligand-gated. We also have pressure-sensitive sodium ion channels. So they open when the pressure changes. And obviously, you know that when sodium channels open, this allows variation in the membrane potential and therefore formation of action potentials. So this is the structure of a Pacinian corpuscle. It has a fiber covered by myelin sheath. These are the nodes of Ranvier which are not myelinated, where the action potential actually forms and propagates. So this is entirely the myelinated nerve fiber. This part is the capsule of connective tissue. It has a non-myelinated segment and several lamella filled with liquid. I usually ask my students to draw and label the Pacinian corpuscle. This is a sample of their answers. In part 3, we're going to consider the following experiments and start to fill in one of these tables. Here you can see we're going to fill in the stimulus that is going to be applied, the state of the corpuscle during the experiment, the recording by different electrodes, the location of these electrodes, the shape of the recording we obtain, the name of the wave, and the amplitude of each recording. So let's start with the experiment. This is the corpuscle again. This is the stimulation device which is going to apply pressure on the corpuscle, and we're going to detect what's happening inside the corpuscle on the fiber inside here by R1, by electrode R1, at the beginning of the fiber here by R2, and further along the fiber by R3. So let's try it. So we apply pressure of 1.5 gram per centimeter square. This is what we detect on R1, on R2, and R3. I'll give you a second just to observe, to look. So we have this wave here, increases rapidly, starts to decrease slowly. This one here on R2 starts as a small hyperpolarization, then continues to the regular shape of an action potential that we know. And this is the action potential that we are accustomed to seeing. And voila, when you remove the pressure, notice what happens. Especially at R1, it returns back to its original shape. Now, if you're wondering what are these lines, these horizontal lines, you should remember that this minus 55, minus 50, usually minus 55 millivolt line or value represents the threshold of depolarization required for the formation of action potentials. You can review document 3 for that particular idea. So now, after watching the simulation, we can fill in the table. So the stimulus is the pressure. The Pacinian corpuscle has been deformed. R1 is located within the sensory receptor of the Pacinian corpuscle and detects this shape, this peculiar, this new type of wave we've never seen before. R2 is located in the first segment of the nerve fiber and shows this wave, and R3 further along the fiber and shows this action potential wave. Now the name of the waves, you're familiar with this one, the action potential. The two new ones, this is called the receptor potential, which is inside the receptor, and this is called the generating potential, which looks just like an action potential, but it starts rather slower. So as for the amplitude of this wave in this particular example is approximately 18 millivolts, because it started from minus 70 and it reached just above minus 55. The rest are 100 millivolts from minus 70 to plus 30 millivolts. Minus 70 to plus 30 millivolts. So next, we will subject the Pacinian corpuscle now to increasing levels of pressure, meaning we're going to increase the intensity of stimulation. Let's first focus on the electrodes R2 and R3. Before doing the simulation, I usually ask my students to give their own hypotheses to what they expect would happen. So what do you expect to happen to the propagating action potential regarding the following properties? Just say fry briefly if possible. So what do you expect will happen to the amplitude? I'll give you a second to think about it. So we're increasing the pressure. What should happen to the amplitude? You can give your own hypothesis, but students usually have the required knowledge to answer and to say that it will remain constant because fibers obey the law of all or none. The amplitude should stay the same. What about the frequency, the number of waves? Now this is something new for students, so you can say whatever you like here. You can say it stays the same, it increases, it decreases, whatever you see is fit. And for the speed of propagation, students should say that it will remain constant. They might say otherwise, but usually they know that it depends on other factors like nature of the myelin, nature of the fiber, I mean the presence of myelin and the diameter of the fiber. So let's start with the experiments. So again, we're going to apply pressure on the corpuscle, but this time we're going to start to increase it little by little. The first pressure is 1 gram per centimeter square, and you notice what happens here. Let me repeat it. We apply the pressure, it's deformed. We notice a small hypopolarization wave here on R2 on the first segment of the fiber, and practically nothing. It remains at rest on R3. So let's record the data. We have the name of the wave on R2, generating potential, on R3 the action potential. The pressure is 1 gram per centimeter square. The amplitude here is, again, let's look at it. It's just below the minus 55, so it's just less than 15 millivolts. And the number of waves, it's just one, but it's not really a generating potential or an action potential, it's just a hypopolarization. So if you said 0, I would accept it also as well. As for the action potential, the same pressure, but still no waves here, so the amplitude is still 0, it's still at rest. Let's increase the pressure further. So we apply stronger pressure. You notice the deformation is more important here. What do you see in this case? We see that we have a complete action potential wave recorded. So let's record the data. The pressure now is 1.5, it has been increased. The amplitude is 100 millivolts with 1 action potential or generating potential, and the same thing here. Great, so we reached the threshold. It's remarkable, it's interesting, but we've seen it before. Let's increase the pressure even further. So now 2 grams per centimeter square. What's happening here? Remarkable. So now we have 2 waves recorded instead of just 1. So again, very interesting. The amplitude has remained the same, but the number of waves has doubled, has increased to 2. How about increasing the pressure even further? So now let's apply 2.5 grams per centimeter square, and what do we get? Now the shape of the wave hasn't changed at all, but what you notice is the number of waves is actually increasing. And you can notice also here that the latency period here is larger than here, just because the electrodes are inserted at different sites. This is located further away from the site of stimulation, so it takes a longer time for the waves to reach. But if we record the data here, we have stronger pressure. The amplitude is still exactly the same, but the number of waves has increased to 3. So let's now focus on the electrodes R1 and R3. So R1 is located again inside the corpuscle, R3 further along the fiber. Let's apply the pressure of 1. We're repeating the same experiment. You notice what happened here. The same result we obtained with pressure 1 gram, no action potential. Now we're seeing that inside the receptor there was actually variation in the amplitude. It was minus 70, it reached all the way up to minus 57, but you can see that it didn't reach the threshold of depolarization. Thus, no action potentials were produced here. So let's record the data. Again, we increase the pressure even further and further and further. So I think I didn't actually add the data here. I'm going to add it later, but the most important thing that we can look at here is that for the receptor potential, the amplitude is variable. It's not saying the same. Let me repeat it again for you guys if you didn't catch that. I went rather quickly through it. So let's look at it again. This is the first pressure. No action potential produced here. The second pressure, higher. Now notice that the amplitude of the receptor potential increased, and this time it exceeded the threshold of depolarization and an action potential was formed. When we increase the pressure even more, what happens? The amplitude continues to increase and we have more action potentials. Let's increase it further. It increases even more and we get more action potentials. So in summary, the receptor potential has a variable amplitude, but the number of waves is always the same. It's only one wave. Whereas for the generating potential and the propagating action potential, the amplitude is constant, but the number of waves is changing. It's variable. So, okay, hi, what do you want? I just wanted to point out that the receptor potential is a graded potential. Graded? What do you mean? It's over. We got a grade. We got a mark over it. Graded potentials are changes in membrane potential that vary in size as opposed to being all or none. So you mean that its amplitude is not constant, so that's why it qualifies as a graded potential. Okay, thank you very much. Very interesting. Now, specify the role of the receptor in generation of action potentials and the necessary conditions. So, what does the receptor have to do with the action potential generation? First of all, the role of the receptor is to receive the stimulus. It is the one which was receiving the pressure, and then it responds with the receptor potential, which helps to generate action potentials. How come? Well, the necessary condition is that the receptor potential must reach the threshold of depolarization in order for action potentials to be generated. Very good. So again, I'll return to this slide here. Thank you. When the receptor potential exceeded the threshold, what happened? Action potentials were formed. The longer it remains above threshold, the more action potentials we get. This is a very interesting idea. Back to the slide, this one. Now the second question, knowing that the sensory receptors send nerve messages to the nerve centers, the brain or the spinal cord, indicate how will the nerve center be able to distinguish between the different pressures? Well, from the different frequencies, of course, of the action potentials it receives. The more action potentials it receives, this means what? There's variation in the pressure is stronger. The conclusions. With respect to the genesis or the formation of action potentials from the sensory receptors, what can we conclude here? Let me give you a second to think about it. Are you ready? Okay, so for the formation of action potentials, the sensory receptor only generates action potentials when its or their receptor potentials reach the threshold of depolarization, minus 55 millivolts. With respect to the coding of the intensity of stimulation, what do we mean by coding here? When we increase the intensity of stimulation, how will the nerve structure translate this change to inform the nerve center? Well, inside the receptor, when the intensity of stimulation increases or changes, the receptor responds by modulation or changing the amplitude of its receptor potential. Whereas along the fiber, it will respond by changing or modulation of the frequency of the action potential waves or the number of waves produced. Very good. So, a quick quiz here. The Pacinian corpuscle is a sensory receptor specialized for which stimulus? I'm not going to give the answer, you should know it. How does the receptor potential change with different stimulation intensities? The genesis of the action potential from a receptor requires that. Well done. The intensity of stimulation is coded by the nerve fiber by. Excellent. And the generating potential differs from the propagating action potential by. You guessed it, well done. Now let's move on to the exercises of the book, probing the documents. The first question, what type of receptor is the Pacinian corpuscle? Now in the book they supplied this document showing different receptors, different natures of stimuli from touch, pressure, stretching, temperature variations, and the different types of receptors and their location. We're dealing with the Pacinian corpuscle, which has a role of detecting pressure, so it's over here. Then the type of receptor is a mechanoreceptor, so it is a mechanoreceptor. Next question. Compare the recordings obtained in document B. This is document B. It's similar to what we have been working with. Then state the characteristics of each potential recorded. First of all, let's start by what I need to mention in the comparison. I need to mention the recording site where I'm actually recording this wave, the name of the wave, the studied criteria and its values and units, meaning the amplitude, what am I looking at, the amplitude, the number of waves, etc. And the variations in these criteria between one group and another. Is it higher, lower, or otherwise the same? Then I will make my conclusions. I think I didn't write the characteristics at the end, but I will say them orally. So let's start. First of all, during the 2 seconds, you can see here we're applying stimulation for 2 seconds. This is the stimulation, the pressure of about 12 grams per centimeter square applied on the Pacinian corpuscle. And this is the timing for 2 seconds. During the 2 seconds of stimulation, the electrode R1, where's R1? Here's R1. So I should say where it's located, which is inserted inside the Pacinian corpuscle. It shows a single wave, this one here, which is called the receptor potential, while both R2, this is R2, on the first segment of the fiber, and R3, further along the fiber, record more waves. You can see here, more waves, as they show 8 waves each, the generating potentials and the action potentials respectively. This is the generating one, this is the action potential. Now, concerning the amplitude of these waves, that of the receptor potential is about 40 millivolts. It starts from minus 70 and reaches approximately here, approximately minus 30, so it's 40 millivolts. While that of the generating potential and the action potential is higher and constant at about 100 millivolts for each wave, starting from minus 70 to about plus 30. Furthermore, the generating potentials differ from the propagating action potentials by having a small hypopolarization wave at their base. So there you have it. What are the characteristics now of each wave? The receptor potential is a single wave, which is a graded potential, as we mentioned earlier. It has a variable amplitude and decreasing with time. The generating potential and the action potentials have a constant amplitude, and it's similar in both cases, but they differ in that the generating potential has a small hypopolarization wave at its base. Okay, the last exercise. In a fiber, the nerve message is modulated in frequency and not in amplitude. Justify the statement. Now, in the book, they supplied this document, this experiment. So you notice here we're applying more and more pressure. This is the receptor potential in electrode recorded by electrode R1. This is the threshold of depolarization here. And these are the recordings on R3, the different action potentials. Notice with the first pressure, it was too small. The receptor potential did not reach the threshold of depolarization. No action potentials were produced. The second pressure was stronger, so the receptor potential exceeded the threshold and we had 6 action potentials here. And then we increased the pressure even more and we obtained a higher amplitude of receptor potential and therefore more action potentials. So they're asking about modulation in frequency and not amplitude along the fiber. Let's see how we're going to handle this exercise. When they say justify, you have to use the data in the document. So in document C, the number of action potentials generated and detected on the fiber by R3 here, because we're talking about the fiber in the question, the fiber, increased from 6 action potentials to 13 action potentials, from 6 to 13, yet the amplitude of these waves remained the same when the pressure applied for 3 seconds, on the Pacinian corpuscle was increased from 1.5 to about 3. Excellent. So what does this show? This shows that the rise in the pressure here induces a rise in the frequency of action potentials, but does not affect the amplitude of these waves. Thus, in a nerve fiber, the intensity of stimulation is coded by what? The modulation or change in frequency of action potentials and not amplitude. And that's it. So we have 2 main ideas in this activity. The genesis of action potentials, the formation of action potentials, which you can see clearly here in this part. They are only formed, action potentials are only formed when the receptor potential exceeds the threshold. And the second one is the coding and modulation of frequency here. When the pressure increases further, the fiber responds by having more action potentials, so the frequency has been modulated, but the amplitude remains the same. And that's all. If you have any questions, you're free to contact me through the comments. And thank you very much.